Chapter 19, Above and Beyond the Periodic Table. There's a riddle at the far end of the periodic table. Highly radioactive elements are always pretty rare, so you may think that the element that falls apart the most easily would also be the rarest of all. That element, number 87, ultra-fragile francium, is indeed very rare, yet one element is even rarer. To explain this, we have to explore what nuclear physicists call the island of stability, which is their best and perhaps only hope for extending the table beyond its current size. The island of stability. As we know, about 90% of particles in the universe are hydrogen, and roughly the other 10% are helium. Everything else, including 6 million billion kilograms of Earth, is ultra tiny in comparison. And in those 6 million billion kilos, the total amount of astatine, element 85, the rarest of all natural elements, is 1 ounce. 1 stupid ounce. To give you some idea of the scale, imagine that you are looking for a particular car in a huge parking garage and you have zero idea where it is. Then imagine walking down every row, on every level, past every space, looking for your vehicle. To mimic hunting for astatine atoms inside the Earth, that parking garage would have to be about 100 million spaces wide, have 100 million rows, and be 100 million stories high. If astatine is so rare, it's natural to ask how scientists ever found any of it at all. The answer is they cheated a little. Any astatine that was originally present in the early Earth has long since decayed away through radioactivity, but other radioactive elements sometimes decay into astatine after they spit out alpha or beta particles. By knowing the total amount of the parent elements, usually elements near uranium, and by performing some calculations, scientists can get a pretty good idea about how many astatine atoms exist. This works for other elements too. For instance, at least 20 to 30 ounces of astatine's near neighbor on the periodic table, francium, exists at any moment. Oddly, even though astatine is much more rare than francium, it's more stable. If you had 1,000,000 atoms of the longest lived isotope of astatine, half of them would decay away in 400 minutes. A similar sample of francium would hang on for just 20 minutes. Francium is so fragile it's basically useless, and scientists could never gather enough atoms of it to make a visible sample. If they did, it would be so intensely radioactive that it would murder them immediately. Most likely, no one will ever produce a visible sample of astatine either, but at least it's good for something, a quick-acting radioisotope in medicine. The odd relationship between astatine and francium begins in their nuclei. There, as in all atoms, two forces compete against each other: the strong nuclear force, which is always attractive, and the electrostatic force, which can be attractive but can also repel if both of the charges involved are positive or if both are negative. Though it's the most powerful of nature's 4 fundamental forces, the strong nuclear force can act over only extremely short distances. If particles stray more than a few trillionths of an inch apart, the strong force loses its grip on them. When it does work inside the nucleus, for example, it keeps protons and neutrons bound together rather than letting the repulsion between positive protons break the nuclei apart. When you get to nuclei the size of astatine and francium, the strong force has trouble holding all the protons and neutrons together. Francium has 87 protons, none of which want to touch. Its 130-odd neutrons help to keep the positive charges apart, but they also add so much size that the strong force cannot reach all the way across the nucleus. This makes francium and astatine very unstable. From all this, you may think that adding even more protons in elements with atomic numbers greater than 87 would make things even more unstable. And it does, sort of. But there's a catch. In the late 1940s, Maria Geppert-Mayer developed a theory about long-lived magic elements, elements with 2, 8, 20, 28, etc. protons or neutrons that were extra stable. Other numbers of protons or neutrons, such as 92, also formed fairly stable nuclei, and that's why uranium is more stable than either astatine or francium, despite its being heavier. As you move down the periodic table, element by element then, things generally get less and less stable, but with some exceptions, as one force gains the upper hand than the other. In theory, magic numbers extend until infinity, until it turned out that there was a semi-stable nucleus after uranium at element 114, flerovium. Just as strangely, elements such as Copernicum and livermorium seemed, on paper at least, to also be somewhat stable since they had close to 114 protons. Even being close to a magic number seems to help. Scientists began calling this cluster of elements the island of stability. Element 87, francium, is stranded between a magic nucleus at 82 and a somewhat stable nucleus at 92. Francium is not only the least stable natural element, it's less stable than every element up to 104. Still, there's more francium than astatine. Why? Because many radioactive elements around uranium happen to decay into francium as they disintegrate. But francium, instead of doing the normal alpha decay and thereby converting itself through the loss of 2 protons into astatine, decides more than 99.9% of the time to undergo beta decay instead and become radium. Radium then undergoes a bunch of alpha decays that leap over astatine. In other words, the path of many decaying atoms leads to a short layover on francium, hence the 20 to 30 ounces of it. At the same time, francium shuttles atoms away from astatine, causing astatine to remain very rare. So what about that island of stability? It's doubtful that chemists will ever make elements with very high magic numbers, but element 114 was confirmed and christened flerovium in 2012, so perhaps they can make a stable element 126 and go from there. Maybe even elements in the 140s, 160s, and 180s are possible, and if so, then the island of stability would become a chain of islands. The thrilling part is that those new elements, instead of being just heavier versions of what we already know, could have weird and wonderful new properties. Reimagining the table. And if they are ever made, the standard castles with turrets look of our table, printed in the back of every chemistry book, is just one possible arrangement of elements. Maybe there will be a new look to the table in the future. Many of our grandparents grew up with quite a different table, one just 8 columns wide all the way down. It looked more like a calendar with all the rows of the transition metals crammed into half boxes, like those unfortunate 30s and 31s and awkwardly arranged months. A few people even shoved the lanthanides into the main body of the table, creating a crowded mess. No one thought to give the transition metals a little more space until Glenn Seaborg and his colleagues made over the entire periodic table between the late 1930s and 1960s. It wasn't just that they added elements, they also realized that elements like actinium, element 89, didn't fit into the scheme that they'd grown up with. Actinium was a key element in giving the modern periodic table its shape, since Seaborg and his colleagues decided to place all the heavy elements known at that time, now called actinides, at the bottom of the table. As long as they were moving those elements, they decided to give the transition metals more elbow room too, and instead of cramming them into triangles, they added 10 columns to the table. This blueprint made so much sense that many people copied Seaborg. It took a while, but in the 1970s, the periodic calendar finally shifted to become the periodic castle that we have today. But who says that's the ideal shape? The columns have dominated since Mendelev's day, but Mendeleev himself designed 30 different periodic tables, and by the 1970s, scientists had designed more than 700 variations. Some chemists fuss with hydrogen and helium, dropping them into different columns. One clever modern periodic table looks like a honeycomb, with each hexagonal box spiraling outward in wider and wider arms from the hydrogen core. Other versions have a hydrogen sun at the center of the table, and all the elements orbit it like planets with moons. Some have mapped the periodic table onto helixes, like our DNA, or sketched out periodic tables where rows and columns double back on themselves and wrap around the paper. We don't even have to limit periodic tables to 2 dimensions anymore. In the end, then, though, there's little doubt that Seaborg's table of rows and turrets, with lanthanides and actinides like moats along the bottom, will dominate chemistry classes for generations to come. It's a good combination of easy to make and easy to learn, But it's a shame more textbook publishers don't balance Seaborg's table with a few of the weirder periodic table arrangements. 3D shapes that pop up and buckle on the page and bend far distant elements nearer to each other, sparking some link in the imagination when you finally see them side by side. I wish very much that I could donate $1,000 to some nonprofit group to support messing with wild new periodic tables based on whatever organizing ideas people can imagine. The current periodic table has served us well so far, but reimagining it and recreating it are important for humans. Truly universal. If aliens ever land and park here, there's no guarantee we'll be able to communicate with them or explain our primary concerns to them. Would they even understand concepts like love, religion, respect, family, peace? Probably the only thing they'll be able to grasp are numbers like pi and the properties of the periodic table. I want them to be impressed with our ingenuity in organizing those properties, and maybe, just maybe, for them to see some shape they recognize among our collection. Then again, our good old boxy array of rows and turrets, with its marvelous clean shape, has served us pretty well so far. It has unlocked the science of everything from stars to giant shark teeth, from medicine to natural nuclear reactors, and there are still new discoveries being made in both the human and the scientific realms. The periodic table is the basis of so many discoveries in chemistry and physics and biology, and it's one of the few things we know of that's literally universal, something that even alien life forms would understand. But the periodic table of the elements is a very human thing as well, a treasure trove of all our passions and obsessions, and I'm constantly amazed at all we've managed to pack in there.